In the last lecture, we talked about trapezoidal and Simpson one-third rules for calculating numerical integrals. These two rules are special cases of what are called Newton-Cotes quadrature. Just to remind you, quadrature literally means calculation of area, and since the area under the curve is what a definite integral is interpreted as, it should not come as a surprise that methods for calculating integrals numerically are officially called quadrature methods. Now, in the Newton-Cotes quadrature, so called because they are really related to what is known as Newton-Cotes interpolation, the basic idea is this: an integral from a to b of fx dx is estimated by doing the following. You first divide the interval from a to b at n points, which means n minus 1 equal parts, and the points, let us call them x1, x2 up to xn, where x1 of course is a and xn is b, and the spacing is h, which is b minus a, the whole interval divided by the number of intervals, which is n minus 1. Just to remind you, the number of intervals is of course one less than the number of points. You do this first, then you approximate the integrand, this function f of x, by a collocation polynomial. We talked about collocation polynomials when we were dealing with interpolation. The basic idea is that this is a polynomial which will go through the points x1, f1, f1 is of course short for f of x1, x2, f2, and so on up to xn, fn. What this means is that instead of looking at all the points on the curve, which of course there are infinitely many of, we are looking at just the n points on the curve corresponding to the n minus 1 intervals into which my interval for integration b minus a has been divided. And what we do is we try to draw a polynomial which goes through each one of these n points. This collocation polynomial, in order to be unique, must be an n minus 1 degree polynomial. And what we then do is estimate the area under the curve, or approximate the area under the curve, which is the integral f of x dx from a to b, by the area under this collocation polynomial. So that's it. When we take only 2 points, that is a and b are my 2 points, I join them with a straight line, because that's the collocation polynomial, the unique collocation polynomial which will go through those 2 points, and we get the trapezoidal rule. When we divide the interval into 2, so that we get 3 points, the left end, the right end, and the middle, and send a parabola through these 3 points on the curve and find the area under the parabola, what we end up with is the so-called Simpson's one-third rule. So it's easy to see that the n-point Newton-Cotes quadrature will be exact for polynomial integrants up to degree n minus 1, because after all we are approximating the curve by a collocation polynomial which is degree n minus 1. If the original function really had been a polynomial of degree n minus 1, the collocation polynomial would have coincided with it. Now, what we can do, of course, is to improve the accuracy of these methods is to increase n. So instead of dividing the interval up into 2 pieces as in Simpson, we could have divided it into 3 or 4 or 10. And if I divide it into 10 pieces, hence have 11 points, I can set a 10 degree polynomial through those 11 points, approximate the area under the curve by the area under that polynomial. But this approach has problems. Of course, the formula for the calculation becomes more complicated, but that really is not the most important problem. The most important problem is that if you try to fit a very high order collocation polynomial, then instead of getting better, the interpolation may become very much worse. This is the phenomenon behind this is called the Runge phenomenon, which we had met when we talked about interpolation. So you can look back at those lecture slides and try to figure out exactly what I am talking about here. But it might so happen that if I try to fit a very high degree collocation polynomial to a given curve, the collocation polynomial might end up swinging wildly, and so the results will be very wrong. So we usually don't do this. We usually don't go in for higher and higher n. What we do is we use a composite Newton-Cotes quadrature. We keep the n small, and instead of trying to do Newton-Cotes quadrature over the entire interval, we break up the interval first into few pieces, and then over each piece we do the Newton-Cotes quadrature. Either we apply trapezoidal rule or Simpson's one-third rule or whatever. And as a result, we end up with a more accurate formula. This is the so-called composite trapezoidal, composite Simpson's one-third, or composite Newton-Cotes quadrature. Frankly, when we usually say Simpson's one-third rule, we mean the composite Simpson's one-third rule. As I said a while ago, in Simpson's one-third rule, you actually divide the interval into two pieces. But if you remember from the last lecture and from the classes we had before, in Simpson's one-third rule, we divide the interval into an even number of pieces. That's because when we are saying even number of pieces, we are talking about the composite Simpson's one-third rule. We first divide the interval up into n pieces and apply Simpson's rule to each one of those pieces. So I now need 3 points within each of those pieces, so 2 intervals in each of those pieces. That's why we need 2n intervals. Now, if the integrand values are available only at equally spaced intervals, and this might very well happen for several reasons, including the fact that the integrand, the function which we are trying to integrate, may be very, very difficult to calculate. So we are only evaluating that at certain special points, or could be because these integrand values are available only via some kind of say experiment, and this is really experimental data, and we want to find the area under the curve for experimental data, and so we can only do a finite number of evaluations. Then this is the best we can do. If the data are available only at equally spaced intervals, then you cannot do much better than using Newton-Cotes. But if we have the freedom to choose the points where we can evaluate our data, we can actually do better. We can have more efficient methods which are more accurate with same number of function evaluations and so on. Let me point out that here, when we say efficient, we mean in terms of the number of times the function has to be evaluated, the function f of x, the integrand. Evaluating that usually is the most complicated or time consuming step in the whole process. So we try to keep that to a minimum. So we can go beyond Newton-Cotes if we have the freedom to choose the point where we are evaluating the integrand. Well, how do we go beyond this? To go beyond this, let us first take a look at what we have been doing so far. In the trapezoidal rule, for the integral from a to b, we of course evaluate the integrand at 2 points, at x equal to a and x equal to b. And this of course gives us an exact result for f of x equal to mx plus c. That's because mx plus c is a straight line, equation for the straight line joining the 2 points at the two ends. And if the integrand had been a straight line function, then what we do in trapezoidal is exact. Well, in Simpson's one-third, we evaluate the function at 3 points, a, b, and the middle, that is at x equal to half of a plus b. And because we have 3 points through which we can send a collocation polynomial, the collocation polynomial we use is a quadratic function which has 3 parameters, one for each of the points. So our result will be exact if we have a quadratic polynomial. Can we find a formula which is more efficient? More efficient in the sense, of course, can you find a formula which works for higher order polynomials? It will just go on to higher and higher number of intervals, higher and higher number of points. But that, of course, is not what we are aiming at. We are saying, by evaluating the function the same number of times, can we do better? For example, can we find a formula that evaluates the function just twice, as in the trapezoidal rule, but actually gives you the exact result, not just if f of x is a straight line function, but f of x is even a cubic function? That's even better than Simpson's one-third. Actually, we can. So this is the idea behind what is called Gauss quadrature. We are going to describe two-point Gauss quadrature in the next slide. This is just a toy model in a sense. Nobody really uses two-point Gauss quadrature in real calculations. Typically, people use 32-point or 64-point Gauss quadrature. But we are going to see what the basic idea is behind Gauss quadrature by starting small, starting with only 2 points. And rather than do the general integral a to b f of x dx to begin with, we are simplifying the calculation a bit for ourselves by choosing the special integral -1 to +1 f of x dx. As we will see soon, this does not impose any real restrictions on us, but for the time being, let's stick to -1 to +1. So the trapezoidal rule for this integral, of course, is this. You take f of x dx, which is approximately, well, this is an approximation, of course, is 2, which is the width of the interval from -1 to +1. The heights of the function at the two ends, f +1 and f -1, averaged. So it's the width times the average height, which is of course the area of a trapezoid. And this of course turns out to be f1 plus f -1, which, as is easy to see, is of the form w1 times f of x1 plus w2 times f of x2. The function is being evaluated at 2 points x1 and x2, and the value of the function at those 2 points are being multiplied by two weight factors w1 and w2. It's easy enough to read off what w1 and w2 are from this expression. Well, w1 and w2 of course are 1 each. That's the multiplying factor in front of both f1 and f -1. And x1 and x2, the points where the functions are evaluated, are +1 and -1 respectively. So we have two weights, 2 points where the function is to be evaluated, and this is basically what gives us the trapezoidal rule. Although we are going to talk about 2-point Gauss quadrature soon, let us just see what our 3-point case is like. That is Simpson's one-third rule. In Simpson's one-third rule, well, we evaluate -1 to +1 f of x dx. By doing this, you take 1/3 of, this is h by 3, remember, and h in Simpson's one-third rule is sides of one interval. In Simpson's one-third rule, you divide the whole interval into 2. This is a basic Simpson's one-third rule I am talking about, not the composite one. And so each interval has size 1, and 1/3 in the name comes because what sits here is h by 3. So it's 1/3 times the value of the function at one end plus value of the function at the other end plus 4 times the value of the function right at the middle, which is this. 1/3 f +1 plus 4/3 f0 plus 1/3 f -1. This again is of the form w1 fx1 plus w2 fx2 plus w3 fx3, where w1, w2, w3 are 1/3, 4/3 and 1/3 respectively. x1, x2 and x3 are +1, 0 and -1. So this form wi fxi summed over I going from 1 to n is a standard form for all the interpolations we have done so far. What trapezoidal rule and Simpson's one-third rule differ in essentially is in the value of the weights and also the number of points involved. Of course, hence the position of the points involved as well. But now let us look at this. The 2-point formula that we used for trapezoidal, weight times the value of the function, actually has 4 parameters. The 2 positions x1, x2, also the 2 weights w1, w2. So we have 4 things to play with. In the trapezoidal rule, of course, x1 and x2 were fixed. They were the 2 endpoints, +1 and -1 respectively. But if we are free to choose those parameters any way we want, including change the positions where we evaluate the function, can't we choose these parameters in such a way that we get an integral which is exact for the polynomial which involves 4 parameters, namely a cubic polynomial, a0 plus a1x plus a2x squared plus a3x cubed. After all, we have 4 arbitrary polynomials to play with here. That is 1, x, x squared and x cubed. These are independent polynomials, just multiplied by whatever constants to get the general cubic polynomial. And we have 4 parameters to play with, w1, w2, x1 and x2. The answer is we can. We need to choose those parameters in such a way that the integral is exact for 1, that is f of x equal to 1, f of x equal to x, f of x equal to x squared, and f of x equal to x cubed. If the integral is exact for each one of the 4 basic polynomials or 4 basis vector polynomials in the linear vector space of all cubic polynomials. I know you have learned enough linear vector space theory to know that the set of all up to cubic polynomials make up a 4-dimensional vector space, with one obvious choice of basis being 1, x, x squared and x cubed. If these 4 polynomials give you exact results, then of course any linear combination of them will, that is any general polynomial which is up to degree 3. I say up to degree 3 because a3 could very well be 0, and then you would not get a degree 3 polynomial. The same expression would be a degree 2 polynomial, or even less. a2 could also be 0. Anyway, if I get exact values for 1, x, x squared and x cubed, I will get an exact value for f of x for any polynomial which is up to degree 3. Well, how do we achieve that? Well, we achieve that simply by demanding this. If I put in fx equal to 1, then w1 f of x1 plus w2 f of x2 must be the integral of 1, with f of x here being 1, which means that the left hand side must become w1 into 1, which is the value of f of x1, whatever x1 is, and plus w2 into 1, w1 plus w2, and the right hand side of course must be this integral, which is 2. Well, that's one equation for the 4 unknowns. If I choose f of x equal to x, the integral must work with f of x1 being x1 and f of x2 being x2. This must be exactly equal to the integral of x dx, which of course is 0. So we get w1 x1 plus w2 x2 equals 0. Yes, the rest is trivial. If you put in fx equal to x squared, then w1 x1 square plus w2 x2 square must give you the exact value of this integral, which is 2/3. And if f of x is x cubed, which is the last demand that I can make, then w1 f of x1 plus w2 f of x2, I'm sorry, is going a bit under the screen here, but you should be able to make out what this says. It says w1 x1 cube plus w2 x2 cube must be the value of this integral, which is again 0. Now, can we go any further? The answer is no, because we have only 4 unknowns to play with, and this has already given us 4 equations. So we have 4 parameters and 4 simultaneous equations, but a rather complicated set of simultaneous equations. Remember, not only are w1, w2 unknown, x1, x2 are also unknown. So we have 4 nonlinear simultaneous equations in this. Now, this is not too difficult to solve, despite the fact that nonlinear simultaneous equations are actually pretty difficult to solve. In general, this particular set can be solved rather easily. Let me just give you a hint. This can actually tell you that w1 x1 is minus w2 x2, and this one tells you w1 x1 cube is minus w2 x2 cube, and unless you want the weight to be 0, etc., etc., you can easily check that this will mean that x1 square must be equal to x2 square, which means x1 and x2 must be negatives of each other. Using that and the other two equations, it's pretty easy to find out the solution. That is, w1 and w2 are both equal and 1, and x1 and x2 are negatives of each other. x1 is plus 1 by root 3, x2 is minus 1 by root 3. And so the 2-point Gauss quadrature formula, which is exact for polynomials up to degree 3, happens to be 1 times f at plus 1 by root 3 plus 1 times f at minus 1 by root 3. So this is your Gauss quadrature formula, which is exact up to degree 3. 2 point, just 2 function evaluations. Well, if we can, we usually don't use just 2 points, we use more points. So if we evaluate the integrand at n points, we can get an approximate formula, which is a weighted sum of the value of the function at those n points at x1, x2 up to xn multiplied by w1, w2, wn. Now, how many parameters do we have here? 2n, right? There are n weights, w1, w2, wn, and n nodes, x1, x2, xn. Why are these called nodes will be clear soon. So these are the points at which the function is going to be evaluated. These are not nodes of the function. Of course, if these had been nodes of the function, then the integral would have been 0. Now, the claim is we can adjust these two n parameters in such a way that we get a formula which is exact for polynomials up to degree 2n minus 1. So if I use 32-point Gauss quadrature, all polynomials of degree up to 63 can be exactly evaluated. Integrals of that can be exactly evaluated by this formula. So if your function that you are trying to integrate is a polynomial up to degree 63, then your answer will be exact. If your function can be approximated nicely by a function which is not too high a degree polynomial, the result will be a pretty good fit. It will not be exact, but it will be a pretty good fit to the exact result. So in principle, we can find the nodes and weights by solving the 2n minus 1 nonlinear simultaneous equations that we can find out. That is, put in, say, demand that this integral will be exact for x equal to 1, which will give me w1 plus w2 up to wn is 2, just like we had before. Then demand again that is exact for x, so I will get w1 x1 plus w2 x2 plus w3 x3 up to wn xn equals 2/3 and so on. In general, what I will get is wi times xi to the power j summed over all possible i's, where j runs from 0, 1, 2 up to 2n minus 1, will give me 0 for odd j, because for odd j, if you are trying f of x to the j, f of x to be x to the j, for odd j the integral from minus 1 to plus 1 vanishes, and 2 by j plus 1 the exact value of the integral for even j. So this will guarantee that for each each power of x from 0 to 2n minus 1, I get the n-point Gauss quadrature formula will give me the exact result, which of course means that the n-point Gauss quadrature formula will give me the exact result for any linear combination of them, that is any polynomial up to degree 2n minus 1. Now, there's only one catch here. The catch here is that we, for a reasonably large n, even for n equals 10 or so, we get a very large number of nonlinear simultaneous equations. Simultaneous part is straightforward, but the nonlinear part is really problematic. In practice, this is very, very difficult to do. This is solving these equations is very difficult to do for a large value of n. The way we get out of this problem is by using advanced math. Now, this part of the derivation is, well, slightly beyond our course right now, so I am not going to go into the derivation, but I will point out to you that you had already met orthogonal polynomials before, in particular the Legendre polynomials, or Legendre polynomials really. The Legendre polynomials are the ones which we use here, and It turns out that the xi's are really the n nodes which the function Pnx, the nth degree Legendre polynomial, has. So which is why we call these excess nodes. They are really nodes, they are literally nodes of the nth degree Legendre polynomial. And the weights are given by some formula here. I am just mentioning this for completeness. We are not going to derive these results here. The derivation is not too difficult but requires a bit of advanced math, some properties of Legendre polynomials and so on. And frankly, we will not need to use these expressions. This expression, of course, is not too complicated. It just says the weights are related to the derivative, the slope of the Legendre polynomials at the nodes. Now, the reason why these equations, where exactly the xi's are and how to calculate the weights, is really not that important for us, is that you can readily find tables in books or on the internet where the weights and nodes for n point Gauss quadrature is tabulated. In fact, you can find results for pretty high values of n, 32 points, 64 points, 128 points. These are pretty easy to come by. Just Google it up. So these tables are readily available, and when we actually go on to program this, we are actually going to use these tables. Well, there's only one thing left, which is this. The formula that we wrote down, Wi f of xi summed over from I equals from 1 to n, with the nodes and weights which we can read off from a table, for example, works fine for integrals from -1 to +1. But what if we don't have integrals from -1 to +1? What about integrals from a to b of f of z dz, where a and b are two arbitrary finite numbers? Well, this is not very difficult. All you have to do is change or substitute variables so that in terms of the new variable the limits become -1 and +1. The substitution is actually pretty simple. If you do this particular substitution, you can note that when z is b, the upper limit, x becomes twice b minus b plus a, which is b minus a by b minus a, that's x becomes +1. At the lower limit, z equal to a, x becomes twice a minus b plus a, that is a minus b by b minus a, that's -1. So this is a pretty straightforward linear substitution that you can do, which will change the interval from a to b into the interval from -1 to +1. And of course, then what we have to integrate is a function of x, not a function of z any longer. And of course, the functional form will change, and to remind us of that, I put a tilde on top. Frankly, most of the time we ignore the tilde, or we ignore to change the name of the function, but we really should do that. This is standard substitution, nothing special is happening here. And so, the integral from a to b f of z dz becomes the integral from -1 to +1, which are the limits of x, of f tilde x dx, with an additional factor of b minus a by 2, which comes from the fact that dx and dz are related by dx is 2 by b minus a dz. And the n-point Gauss quadrature formula can now be easily used, because this integral is the one for which we know how to use the n-point Gauss quadrature formula. So we get b minus a by 2 times this integral from -1 to +1 is replaced by the n-point Gauss quadrature formula, Wi times the value of the function f tilde at each xi. Well, f tilde at each xi is really f at the corresponding z. So in terms of the original function f, this formula simply becomes this: b minus a by 2 sum over I going from 1 to n, Wi times f at the z value corresponding to xi. So for each x, the z value is b minus a by 2 into x plus b plus a by 2. So this is the final formula. If you are using NumPy arrays, for example, manipulating this would be rather trivial to do.